Good morning. This is our third session for the recorded lecture. Before I begin the lecture, I would like to explain a few things. The recorded lectures would be different in terms of format, in terms of one-on-one relationship that I would build inside the classroom. So the classroom would be a lot more interactive, and everybody would get a sense of the direction. But inside the recorded sessions, often we cannot explain a few things that we would normally explain inside a regular classroom. Regular classroom enjoys a bit of a privacy because it's limited to the environment, but the recorded session has to go public. So in that sense, you might miss out if you just listen to the YouTube. A study has shown that attendance is the #1 factor in the success of everybody involved. So please do try to attend. These recorded sessions are meant only for those who are at the distressed situations and would like to take advantage of the possibility to go over the material once again. Now, we are at chapter 3. The agenda today is going to be on nodal analysis. I'm going to cover a number of examples. Then I'm going to go into the supernode, a bit of a challenge with the supernode and how we are going to handle that. It's not really that difficult. As long as we have the right imagination, we should be fine. Then we have mesh analysis, a number of examples follows, and then super mesh, and that will complete chapter number 3. But along the way, I'm going to have a number of examples to clarify the topic and concepts. So what did we do in chapter 2? And in chapter 1, of course, we talked about variables. We defined the voltages and currents, the power, and then the way they relate. Then we went into chapter 2. We talked about the component law, specifically a resistor, which follows the Ohm law. And in this class, we have assumed that the resistor is a fixed resistor, does not change in time, does not change with temperature. So basically, it's a linear component. And then we went into the topology laws, and we said how we would identify components that are attached in parallel or in series. At the end of chapter 2, what we did was to put two components in series and create a combination suitable for basically voltage division principle. We said that the currents in series would be exactly the same, and the voltage, if they are in series, can be identified by the ratio of resistors, R. We called it R rule to make it easier for us to refer to. Then we put the resistors in parallel, and we identified that the voltages of components in parallel would be exactly the same. At the same time, we said that if they are in parallel, and you can verify that there is nothing else is going to come in between, you can actually identify the currents according to the G rule. The G rule means that the current of a specific component is going to be proportional to the inverse of the resistance. It's 1/R, and that's why we call it the G rule. When we have two components in parallel, the textbook and everybody else says that you can actually simplify the G rule. Two components in parallel can be replaced by one component in the following fashion. For example, you have R1. Let me just refresh the memory. If you have this one and you have this, these two are in parallel, R1 and R2, and you would like to find R equivalent. Back in chapter 2, we mentioned that in order to find R equivalent, you have to look into the inverse. 1/R1 plus 1/R2 is equal to 1/R equivalent. So there is a warning here. You have to inverse R1, you have to inverse R2, you have to sum them up, but when you get to this stage, you have one more inverse to do. So that's why many actually forget about this last inversing action. This formula is easy, modular. If you have another resistor, you can actually extend that by 1/1/R3, plus if you have R4, 1/R4, and the list goes on. That's why this is good for us in a general sense. But then you put only two resistors in parallel, you can actually benefit from a simpler knowledge. You see, this is going to be common denominator, and then when you divide this common denominator by this, you get R2 on top, and when you divide this divided by R2, you get R1 on top. And since I'm conscious to do an inverse, many textbooks actually say that if you happen to have two components in series, in parallel, all you have to do is to actually multiply them and divide it by the summation of the two resistors. This rule is only correct for two components in parallel. You cannot extend this for three. So that's why I would strongly advise that everybody follow the modular formula in order to find the R equivalent for that. But you see, when we attacked each of these systems, this is what we did. We wrote component laws, we wrote topology laws, where we would be discussing KCL and KVL laws. That normally gives us a system which is quite huge sometimes. Depending on the number of nodes, number of loops, number of components involved, this could explode to as much as 20 by 20, 100 by 100, and it's going to be out of hand. It's not easy to resolve. So the area we are going to talk about is nodal analysis. While mathematicians helped us understand how to solve the system, we are going to actually grab the concept and modify the basically our understanding of this circuit approach and get to the nodal analysis technique. We are going to say you can actually use even Gaussian elimination that you would normally use for system reduction to get to the nodal analysis. So that's what we are going to do today. Well, let me go on with my traditional technique. In a traditional sense, which is chapter number 2, what I would normally do, the first thing I would do is actually come in and say, how many components do you have? You have two current sources. I identified them as IX and IY. You have three resistors. Well, for each component, you ought to have the necessary variables. So if this is a current that is given to us and known, all I have to do is to actually assign a voltage. So I'm going to say this is Vx. This current is given and known. The value of resistors are also given to us, known. So this is going to be Vy. The red ones identified unknown to us. So when I get to R1, I'm going to have a voltage assigned to it. R2, I'm going to have a voltage assigned to it. And R3 also. Intentionally for resistor though, the situation is different. As soon as you pick up the voltage, the current is not yours to do, because the current follows the Ohm law. If you assign the currents however direction you like, the voltages are not yours because they follow the Ohm law. When I say that the voltage of R1 is plus on top and minus at the bottom, the current has to go from plus through the component and basically leave the negative node. That's what the Ohm law says. In this case, plus, minus, and the current has to go this way. So this is going to be I2, plus, minus, and the current has to be this way. If you are free initially, you can obviously assign the voltages anyhow you like, but then the current of resistors are not yours. The same thing is true. There are some freedom initially, but eventually you are locked into the Ohm law, and you have to follow that in order to be safe. So let's take a look at this system. How many unknowns do you have? For every resistor, you're going to have two unknowns. So you have 6 unknowns already. You have one unknown for this voltage, one unknown on this, you have 8 unknowns. If I go by chapter 2, I would really need to have 8 equations, 8 unknowns. Let's see if we can get that far. So first, very simple, I'm going to do a modular approach. I'm going to write the component law. I'm going to say whatever laws apply. Then I'm going to say topology law. And topology laws are going to have KCL laws and KVL laws. Components law are really easy. You have 3 resistors. Since you have followed the Ohm law already, it's really easy. You can even close your eyes and write it down. You can say this is going to be V1 as equal to R1 I1. V2 as equal to R2 I2, the index hopefully follows what we have done on the graph itself, on the circuit itself. Okay, so that's going to be my component law. When I get to the KCL law, I need to know the nodes that I need to write the laws for. So first, how many nodes do I have? I have one node here, one node there, and one node here. This is a big node. This is one node. This is a combination of wires, and you can actually squeeze this and basically make it just one node. You can actually put your hand across and grab it down. You can see there is a single node here. So if I say this is one node, this is second, and this is third. So what I'm going to do, from among the 3 nodes I have, according to the discussions we had in chapter 2, I'm supposed to pick up one of them as my reference node. So I'm going to say this is N0, and I'm going to call this reference node. Many textbooks simply say this is ground and ground this. But as we have learned in lab number 2, ground is different from a reference node. Then I have N1 and I have N2. So how many nodes are left for me to do KCL law? I have 2 nodes, and I need to follow the simple convention we agreed upon, and that is any current that is entering the node is going to be negative, any current that is leaving the node is going to be positive. Let's stick to that convention for us. You have 2 nodes. For node 1, you are going to have, for node 1, how many components do you have? Everything should come to your eyes in a flash of light. You have 1, 2, 3, 4 components attached to node 1. You need to see 4 terms. So in that sense, Ix is actually entering the node. You can follow your hand. So Ix is going to be negative because it's entering the node. I1 is leaving the node. I2 is leaving the node. Remember, this is the node and I2 is leaving. And Iy happens to be leaving the node as well. So that's my topology law, KCL law. Remember, topology law has nothing to do with the component itself at this time. It's simply about interconnectivity of the components. Now when I get to node 2, I'm going to see how many components are attached. 1, 2, 3. I need to see 3 components, 3 terms for node 2. For node 2, I see Iy is entering the node, that's why it's negative. I2 is entering negative, I3 is leaving positive. So it's going to be minus I2 plus I3 as equal to 0. Okay? So I finished my KCL law. Then I have to do my KVL law. The KVL law, you need to identify the loops. Well, obviously there are so many loops, but we said in order to write KVL law safely, you need to pick up the primitive loops or the basic loops. And the basic loop would be this one, that's 1, 2, and 3. Obviously you can identify more loops, but they are not basic because, for example, this loop has 2 basic loops inside. This loop has 2 basic loops inside. When I pick up this, I don't see any other loop inside. That's why it acts like an atom. It's the basic building block of the structure. So I have 1 loop, 2 loop, and 3 loops. If you remember the convention we agreed upon for us as markers and for you to get the hold of it, we said that always pick up the loop and then pick up the direction according to the clock. And in this sense, I'm going to go clockwise and I'm going to assign this as my direction. So this is D1, this is going to be D2, and this is going to be D3. Because it's a small circuit, I couldn't do it, but generally speaking, I would like everyone to actually draw this as large as possible so that you don't miss out on any components. Let's do D1. On D1, you have 2 components in loop number 1, this and this. Because this loop consists of 2 components, you need to give me two terms. So let's go for D1. Let's begin from one end, say from this end. The head of the arrow comes in. The first thing it sees when it catches component Ix, the first thing it sees is a minus polarity. Then it goes through the component. So it's going to be minus Ix. It continues its trip. The next time when it meets the new component R1, it's going to hit the plus polarity, and that's why we call this V1, and this is going to be equal to 0. Two terms, two components, and done. Let's do D2. Let's begin from a simple node, say here, simple position, say this one. I'm going to follow the arrow of this loop in this direction. The arrow comes in, visits R1. The first thing it sees on R1, it sees a minus polarity. This minus is here as well, so there is no harm in that. So this is going to be coming in, it's going to see the minus polarity, and as such, I'm going to say minus V1. Then it trips, it goes through the loop, it sees component R2, it sees the plus polarity next. So it's going to be plus V2. On its trip, it's going to come to R3, it's going to see the plus polarity, so it's going to be plus V3 as equal to 0. Okay? So I had a loop. This loop consists of 3 components, and I'm going to have an equation with 3 terms. Let's go for the last loop, which is D3. I have 3 components in that loop, and I'm going to do the 2 terms. I'm going to begin from here, for example. As the arrow comes in, hits the plus polarity of Vy first, go through the component, when it sees R2, hits the minus polarity next. So it's going to be plus Vy minus V2 as equal to 0. Well, at the beginning, what we said is this. We said that you have 8 unknowns. If you take a look at this, you have 1, 2, 3, 4, 5, 6, 7, 8 equations. It seems to be safe to assume that you have enough number of equations to solve the system. Some of the solutions you can actually identify immediately by the concept we discussed before, and that is, for example, Vy and V2 are the same because they are in parallel. If you solve this system, Vy and V2 would be the same. So often we don't go that extra length to just introduce new variables and introduce new equations. We try to benefit from this knowledge. For example, Vx and Vy, they are in parallel. Therefore, Vx is equal to Vy. Vx and V1. So where is that? Now, by the way, this one is not right. This one is Vx. This one has to be voltage. The nature of these two have to be the same. If this is voltage, this has to be voltage. If this is current, everything has to be current. So D1, we need to write minus Vx plus V1 as equal to 0. Okay? Now, what next follows is that I'm going to solve these guys. I'm going to put them inside this equation. I'm going to shrink the system, possibly come to one equation, one unknown, and each time I'm going to find one unknown. And then I'm going to find I1, I2, I3, as well as V1, V2, V3, and Vx and Vy. So this is going to be a heavy process each time if you wanted to do. However, there is a simpler one. And in order for me to achieve that, first I need to define the variable and the way they can be referenced. Take a look at a single component. For example, a resistor. This resistor has 2 ends. In one end, I'm going to call it node A. In another end, I'm going to call it node B. Well, it's going to be connected to so many other components, but of course I'm going to actually see if this component eventually goes into a loop. Let's assume that you have this component attached in a loop of this nature, this one. Let's call this Z1. Let's call this Z2. Let's call this node NC. In chapter 2, what we are going to do, we are going to assign polarity to the voltages. So this is going to be V1. I'm going to assign this polarity. This is going to be V2. I'm going to assign this polarity. This is going to be V3. If I wanted to write KVL law, and it doesn't matter whether I have 3 components or 10 components in a loop. I may have 3 components in the loop. I may have 20 components in the loop. Let's just have a very simple case in front of us, and that is a resistor and 2 more components and 1 simple loop in front of us. So take a look at this. In chapter 2, what I'm going to do, I'm going to assign a direction to this loop. If I begin from this end and I start writing this equation, I'm going to have minus V2, because it hits the minus polarity first, plus V1, then it's going to be plus V3 as equal to 0. Now, if I wanted to see the relationship between V1, V2, and V3, I'm going to extract V1 from this equation. I'm going to put V2 to the other end is positive, V3 to the other end is negative. This is telling me something which is going to help me to begin a specific definition. The voltage of this component with the polarity considered is equal to the voltage of this component minus the voltage of this component. Now, I'm going to say that perhaps there is a way I can break this up into a different variables. This voltage is equal to this voltage minus this voltage based on the polarity I have. As soon as I say this versus sum, I introduce the node voltages. So this is component voltage. The component voltage is going to be fixed, but then I'm going to have this node a voltage assigned to versus a reference node. This node a voltage assigned to versus a reference node. Now that's the important thing. This simplest step, which seems to expand the component voltage to me, actually is going to simplify my system a lot. So I'm going to say, let's see if we can have component voltage mapped into node voltages. In order to do that, let's define what a node voltage is. Whenever you happen to have a system in front of you, you need to pick up a reference node. Let me actually give you an idea as to what we mean by component voltage versus node voltage. A simple daily issue that we might have faced quite a number of times since childhood is to actually measure the height of a baby or an individual when you go to see a physician, family physician. Now, my height is the same. My height is going to be a specific number, whether I'm actually moving around, whether I'm going to be on the desks, as long as I'm rigid in one sense, as long as I'm standing on the ground, regardless of where my position is, my height is going to be fixed. That's going to be the component voltage. That's my specification. However, you can measure my height in different scenarios. A simpler one would be to have a measuring tool, and then you put one side of the measuring tool under my feet, and the other side comes onto the top of my head. So that's how you would measure my height. But also, you can actually measure my height differently. If I'm actually standing on this chair for any reason, suppose that I'm standing on this chair. In order for you to measure my height, not only you have the luxury of measuring my height from my feet to my head, you can also say, using laser meters, You can actually put find the height of my head toward the ground and the height of my feet toward the ground, and if you subtract this, you would get my height. Here is what I'm going to define. My height is a component voltage. The height of my head to a reference node, which is ground, is the voltage assigned to this node. And the height of my feet to the ground would be the voltage assigned to my feet. So in that sense, I can say that component voltage is equal to the voltage of node A in respect to a reference node minus node B in respect to a reference node. You might come in and choose a different reference node. For example, if you choose the reference node which is basically the ceiling of this room. Again, you can say this voltage in respect to the ceiling and this voltage in respect to the ceiling. So that's going to be how you can measure my height. As soon as you have a system in front of you, you are going to actually pick up a reference node. If I pick this one as my reference node, which is actually the same as what you will see here, this is going to be my 0. I'm going to pick up the reference node and I'm going to assign 0 voltage to the reference node. Previously, all I did was to ignore writing case yellow for reference node. Now reference node begins to make a sense to me. This is a 0 voltage. If I wanted to manifest this component voltage in respect to the voltages on the two nodes, I'm going to say V1 is equal to V2 is voltage of this node versus the 0. So it's going to be obviously V2 minus V3. Obviously we did that through the KVL law, but I'm going to rewrite this differently. I'm going to write V2 as A versus 0. And I'm going to write V3, which is this one, as B versus 0. And I'm going to write V1 now as A versus B. Generally speaking, when I want to look into V1 considering the polarity, I can always say V1 is equal to the plus side minus the minus side. So that's the way I'm going to identify now. If I had been successfully able to break up the component voltages, I'm going to show you what happens in terms of the system of equations. But you can keep in mind whatever we just did and discussed on this simple loop is actually, you can see it on this side. For example, D2, if I begin having this type of conversation, I actually satisfied this already. So, in one sense, going from component voltage to the node voltage, you are going to satisfy all the KVL law. In that sense, I don't have to write this. I'm going to take care of that automatically. Okay? Now, one may ask this simple question. If you know the voltages of the nodes, how would you know that the system is resolved? Okay. If I have this 0, and if I have this voltage in respect to 0 known, for example, 10 volts, and if I have this voltage in respect to 0 known, say 8 volts, do I know V2? Yes, V2 is 10 minus 8. Do I know Vy? 10 minus 8. Do I know V3? 8. Do I know V1? 10. Do I know Vx? 10. I have all the voltages. Now how about the currents? Because I know what V2 is, and V2 is going to be 10 minus 8, because I know what the resistor is, then I'm going to know what I2 is. Therefore, instead of having so many, you can just look at the schematic and just feel it. Instead of having so many unknowns that I have, if I know this voltage and this voltage, not only I know the voltage, but I also know the current. V1 minus V2 divided by R2, that's going to be I2. So let's make it simpler. Let's go back and make it a lot simpler. I'm going to remove everything. Okay, Actually, before I do that, let me finish one step before I do that. So let's go and have my original circuit. I want to show you something. If we go by the node voltages, we took care of the KVL law. How about this and this? Let's grab I1 from this and put it in this equation, I2 and I3, and get rid of this set. Let's see how my equation is going to turn out to be. Let's go in. Okay, KVL law will be taken care of. As soon as I do that transformation, I'm going to say N1 minus Ix. I1 is going to be V1 R1. I2 is V2 R2. Iy is of course known. No rush in that. Iy is known. I2 is going to be V2 divided by R2. I3 is going to be V3 divided by R3 as equal to 0. I put the component law into my KCL law. That's the shape. So I took care of 5 and reduced it to 2. If I do that transformation I was just talking about, I'm going to actually take care of this KVL law at the same time. So let's put the KVL law in. Let's do the transformation. For V1, I'm going to say V1, VA minus VB. Let's label this now in a different way so that we don't mix them up. This is, I'm going to label it as A, I'm going to label it as B, and let's begin. Minus Ix. Remember, as soon as I change the component voltage to the node voltage, I'm going to take care of this guy. When I want to say V1, V1 is the plus side minus the minus side. It's VA minus 0. So it's going to be VA minus 0 divided by R1. When I want to say V2, I'm going to say the plus side minus the minus side, VA minus VB divided by R2. And then I have Iy as equal to 0. I'm moving from component voltages to node voltages, having done and taken care of the KVL law. So that's one. Let's remove this. Let's take a look at the second one. Minus Iy minus V2. V2 is the plus side minus the minus side is A minus B divided by R2. I want to put this in a bracket for the safety reason. V3 is B in respect to the ground. V3 is plus side that is attached to B, minus side is attached to 0. So V3 is going to be VB minus 0 divided by R3 as equal to 0. The claim so far is you took care of the component law, you put them into the KCL law, you transform from voltage of the components to the voltage of the nodes, you took care of all the system. Instead of solving 8 equations, 8 unknowns, all you have to do is to solve 2 equations, 2 unknowns. The challenge, however, is this. Am I supposed to write all the KCL law, all the KVL law, all the component law, and then go through the system reduction techniques, whatever technique it might be, to get myself into this equation? Or is there a very simpler way of looking at it? I want you to take a look at this for a moment. This is correct. This is true equations that are needed to solve the system. But if you take a look at these 2 equations, a bit of a similarity comes to life. If you take a look at the first equation, you see VA. This equation is actually for node A. VA is positive, VA is positive, everything else possibly is negative. VA is positive. If you take a look at this equation is actually coming from node B. In node B, if you see, first of all, this VB is positive. This VB, if you take a look at this minus and this minus, that becomes positive. So the similarity between these two becomes evident. And that's what the engineering are going to take advantage of. They're going to say you can actually write these equations in a robotic sense without looking at the entire set of equations. You can write this in the following way. Here is what we are going to do in terms of writing that equation. I'm going to erase this. I'm going to hold this as what we came through a long and difficult journey of calculations, but I want to erase this and show you a different way. Okay? You have a design. In this design, you have a number of components, a number of nodes, a number of loops. You need to identify the number of nodes. You have A, B, C. This is nodal analysis. It's node we need to identify. So you have A, B, and then you have a reference node. This reference node has a 0 voltage in mind. What I'm about to explain might be true in a transient sense, but you don't have to worry about that picosecond, femtosecond that things happen. I'd like you to actually follow my lead and see what I'm trying to do. It's just a kind of a game I'm trying to play so that actually I can write these equations a lot better. I want to be an electron. I am a very small, basically, item, a very small component, electron. Electron is sitting on this node. Because I'm too small, I'm going to be self-centered. I'm not going to see what is happening around me. Because of that, I'm going to assume this is the biggest voltage. I'm actually offering the biggest voltage of the entire design. If this is the biggest voltage of the entire design, unless things are forced upon me by current source, I'm going to say everything is leaving from my node. Okay? So let's write it down. This one is entering the node for node A. I'm trying to write node A. This one is entering the node, so that's minus Ix. Iy is leaving the node, so that's plus Iy. Then I'm going to say this is biggest. This is the king. This is the biggest voltage, and everything else I can imagine would be smaller than me. It's not true necessarily. At the end of the day, the solution of the system will tell me if it's true or not, and that's the stable scenario for the system. It's just going to be a game I'm playing so that I can write the equation a lot faster. This is biggest, and therefore A minus B divided by R2. VA is the biggest, VB is the smallest, and the current is leaving me. That's why I have a plus behind, and that's going to be R2. When I take a look at this, A is the biggest. Obviously 0 is a small. So it's going to be A minus 0 divided by R1. And the current is actually, in my mind, is leaving R1. So it's going to be VA minus 0 divided by R1 as equal to 0. Unless the currents are forced upon me, whether they are entering or leaving, I'm going to assume everything else is actually moving away from the node. A bigger minus B divided by R2, A minus 0 divided by R1. That's my node A. Let's do node B. You don't have to watch my equations, original one. I just want you to watch what I'm trying to do in this case. Now, this is another electron, another me, and that another me is actually sitting on node B. When I look at node B, I'm assuming this is the biggest voltage of the system. It's just an assumption which is obviously not right, but it's helping me to write the equation. This is the biggest one. Unless the current is forced upon me onto the node, every other currents are actually leaving the node. So in this case, current Iy is entering the node. When I get to R2, I'm saying VB is the biggest one, and VA is obviously smaller, and therefore the current in this node is going to leave it this way. So it's going to be R2. And then when I get to this component, I have three components. VB minus 0 divided by R3. VB minus 0 divided by R3 as equal to 0. I made some silly assumptions, and I wrote these two equations, but I want you to compare these two with these two equations. The first one, minus Ix plus Iy plus VA minus 0 divided by R1, VA minus VB divided by R2 as equal to 0. The second one is minus Iy plus VB minus V0 divided by R3, so far so good. And this one is actually the same as this. The only thing that happens is that there is a minus sign. With this simple approach, I can actually write the equations off the chart. I don't, when you take a look at this, I'm not assigning any voltages. I'm not assigning any currents. The circuit is just as it is. In chapter 2, I have to assign currents, directions, polarities, everything. In Nodal, I'm not going to assign anything. I'm going to ignore it, even if it exists on the system. I'm going to ignore it. For example, you go into the exam, and the exam says, solve the Nodal and tell me what is I1 that is shown on the circuit. I'm going to ignore it. That I1 is ignored until the last stage. So let's go. I want to give you a number of examples so that you feel good about how to write the Nodal equation for the system. The next thing we usually want you to do, actually I would like to explain a bit about what we expect you to do in exam, in quiz. When we ask you to simplify the system, we mean that we would like you to rearrange and make sure that the system is represented in a two equations, two unknown, properly ordered. For example, I'm going to say VA is my unknown. I have 1 over R2 and I have 1 over R1. Then I have VB. Intentionally I'm going to say VB though, but I'm going to have minus 1 over R2. And then Ix and Iy are known to me, so it's going to be Ix minus Iy, and I'm done. Take a look at this one. I need to maintain and preserve the same order. That's a system of equation. So I need to take care of VA first. Minus 1 over R2. Then I have VB. VB is going to be 1 over R2 plus 1 over R3. And then I have Iy, which is fixed to me, known to me. This is what I ask you to come into. This is simplification process. Now, if you are using a specific calculator, and please do so, is that you don't even have to say 1 over R1 how much it is, 1 over R2 how much it is. You can actually set the calculator into the equation mode and simply say 1 over 4.7 plus 1 over 6.8. Just punch in the number. Don't waste time onto simplifying this and writing it as one simple number. It's going to take your time. Any moment that you can say, please do. So I'm going to have the calculator set in, put this in. Even when I get to say 10 minus 8, well, it's an exam, it's a stressful situation. Just simply say 10 minus 8 on your calculator. And the calculator is going to actually take care of that. That way you are safe. That way it takes you a lot less time, and you simply solve the system. Now, your calculators are supposed to handle a 2x2 and a 3x3 linear systems. You need to learn this before you come in for the quiz or the midterm or the final. That's going to be a lot helpful. So if you get to this stage and you say I put all the numbers in and simply I got VA as equal to this and VB as equal to this, it's fine with us. It's fine with us. You simplified it and you utilize your calculator and you go on. Now, if you take a look at this entire process in terms of grading, one thing you have to know, and that is you have to make sure that this is actually laid out correctly. If I make a mistake on this, that mistake is going to be considered fundamental mistake, because that mistake is going to go all the way there. If you don't make a mistake here, and if you don't make a mistake here, but you give us some numbers which is not correct, that's going to have its own weight, which is typically a lot less than the entire grade assigned for that question. So this one is going to be 2 marks, this one is going to be 8 marks, and this one is going to be 4 marks, for example. So that's the way we actually ask you to utilize the entire process. You need, though, this sometime, because in question in midterm number 1, we give you the same circuit and we ask you to attack the same circuit 4 times from different techniques. So that's going to be helpful in the sense that you can actually assess yourself right inside the midterm exam. That's why these numbers are important, because question 1, it says VA is 10 volt, VB is 8 volt. Question 2, regardless of the technique you use in this class for linear stuff, you need to get the same number, 10 and 8. 10 and 8 question 3, possibly 10 and 8 question number 4. That's going to be the important stuff. So that's something else. Let me actually go in, and now that we have come to understand how the system is going to be utilized, I'm going to actually go in and attack 2 different circuits and write them down. In the class, I'm going to stop as soon as I write the equations, but at home, please go all the way in order to solve the system and get your numbers basically figured out. So you have 1 amp. This is page 85, practice problem. Then it's going to be 1 ohm, 2 ohms, sorry. And then it's going to be 6 ohm. And then 7 ohm. And then 4 amp. Okay. Chapter 2, what would you do? In chapter 2, you have to assign voltages and currents. You have to identify loops and nodes. You have to write so many equations, so many unknowns. Chapter 3 says you can do it. You can actually have the simpler system in front of you. How many nodes do I have? That's the important question you need to ask. And that's why some of the mistakes come in. You have 1 node here. This is the meeting place of these 3 components. You have 1 node here, the meeting place of these 3 components. And you have 1 node here, the meeting place of 4 components. This is not 2 nodes. This is 1 node. That's where the mistake is. So I'm going to assume this, typically speaking, I'm going to assume the negative pin of a voltage source as my ground or reference, if I have only 1 voltage source. And if there is no voltage source in the design, I usually pick up the bottom line of the circuit as my reference node. So this is going to be VA, and this is going to be VB. Again, we are not kids anymore. As soon as I see VA, I see 3 components, I need to see 3 terms. VB, I see 3 components, I need to see 3 terms. So let's begin for node A. I'm going to assume VA is the biggest voltage of the entire design. That's the king of the entire design. So it's going to be 1 amp is actually entering the node, and I have no option but to accept that. Please note, when I write nodal equation, I'm actually writing KCL law for the nodes. The nature of the terms are amp. Please don't make this mistake I made just a few minutes ago. If you write an equation and one of them is amp, another one is voltage, you are in big trouble, because you can't add apple and orange together. They have to be all apples and they have to be all oranges. You have to be careful on that. This is amp. -1 entering the node. Plus VA is bigger than 0. -0 divided by 2. Plus VA is bigger than anything in the system. VA minus VB divided by 6 is equal to 0. This current goes through this from A, which is the biggest one, to B, which is the smaller one. It's just in my imagination, simply to write the equations and then begin solving it. So this is node B. In node B, I have 3 terms, 3 components and 3 terms. 4 amp is actually leaving the node. When I get to VB and 0 and 7, VB minus 0, I'm assuming VB now is the biggest one. VB minus 0 divided by 7, VB minus VA divided by 6 is equal to 0. Again, when I wrote this one, you might ask yourself, how come you have current going this way and how come the current goes this way? It's just a silly assumption which helps me to write the equation. Eventually, at the end of the day, I would know how much this is, I would know how much this is, and I would know where the current goes, which direction it does, how much the value is. As soon as I know the voltages of A and B, I have everything I need to know for this design. The next stage is to extract all VAs, extract all the VBs and the constants to the right-hand side, and in a very same order, all the VAs, all the VBs, and constants to the next side of the design. Let me go in and basically try one more example before I go into supernode concept. Okay, so let's see. Suppose you have the following design in front of you. This is 10 volts, 2 ohm. Just to follow what the book says, I need to make sure the polarity is the same. So this is plus, minus. This is a question 3.18, but I'm trying to attack this circuit from two different mindsets. The first mindset is that I can actually simply write the nodal equation. So that's 8 ohm, 2 ohm, 5 amp, and 4 amp. If the ground is not given to you, and in this case no one has given the ground to me or the reference node to me, ask of yourself, how many voltage sources do you have? If you happen to have only one voltage source, where is the negative pin? The negative pin is this one, so I'm going to assume this as my reference node. That's going to force this one at 0. If this one is 0, how much is this? That's the question we are going to answer in a moment. How many nodes do you have? You have one node here, and one node is this one. This is all short wires. Okay? So you have node A, you have node B, and of course you have node C. If this is 0, take a look at the 10 volts. The 10 volt is actually attached to the ground and C. I'm going to say the 10 volt is equal to whatever the node attached to the plus side minus the node attached to the minus side. This is my rule, and I will always apply this, and please you too as well apply this simple rule. The plus side is VC. The minus side is 0. And therefore, VC is equal to 10 volts. What I just did, before I even write the equations, I actually found the voltage of a node. This voltage, this node has the same voltage as 10 volts. What's the purpose of writing the nodal equation? When you write nodal equation, you're trying to find the voltages of the nodes. If you know what the voltage of that node is, you don't necessarily have to write the KCL law for that, the nodal equation for this. Since you know this voltage, you don't have to. You may have to later, but at this stage, you don't have to write for this 10 volt. If you are tempted to write the KCL law for this, you need to define a new variable, and this new variable is going to be called Ix. Because when you write the nodal for this node, you are attacking the currents. It's going to be 10 minus A divided by 2, 10 minus B divided by 8, but also plus Ix is equal to 0. The nature has to be the same. Some of us make a mistake and say plus 10 is equal to 0. That doesn't make sense. That's 10 volts, and these are currents. You can write KCL for this, but you don't have to. So that's why I'm going to actually ignore this process for now. What just happened? I had a circuit in front of me. I had only one voltage source. I looked into the negative pin and I grounded it. Because that voltage source is very fixed to me and the value is known to me, I basically went into the simple component versus the node, voltages of the nodes. Component is 10 volts, is equal to the voltage of the plus side minus the voltage of the minus side. The plus side is attached to VC, the minus side is attached to 0, and obviously VC is going to be 10. I know this voltage, I don't have to write the KCL for this. So far so good. So what is left? I have two equations to write, A and B. Let's begin A, node A. I'm going to assume a silly assumption. I'm going to assume that this voltage is the biggest voltage of the entire design. So it's going to be, when I see A, I see three components, and I'm going to see three terms. 5 amp is actually forcing itself to the node, and therefore it's going to be minus 5. Then I'm going to have VA minus 0 that happens to go across the 2 ohm, and obviously my idea is this current is leaving. This minus this divided by 2. This minus this divided by 2 again. So this is going to be plus VA minus, if we are conscious enough, VA minus VC divided by 2 as equal to 0. Let's go for node B. I have three components attached to this. I need to have three terms for node B. 5 amp is leaving the node. VB minus VC, you see, VB minus VC divided by 8, VB minus 0 divided by 4. That's the way I'm going to see this, the set of equation. VB minus VC divided by 8. VB minus 0 divided by 4 as equal to 0. Two equations, two unknown. If I happen to know what A and B's are, I know everything about this design. The next step, would be to extract VAs, extract VBs, and solve that. In this case, apparently, it's just each of one of them happen to be one equation, one unknown. But no, that's not the general sense. All the time, usually, most of the time, you get two equations to unknown and you need to solve them. But happening, this one is VA only, and this one is VB only, which is very simple to solve. That's going to be the nodal equation.